Hello, my name is Kevin Tenney, and I'm a graduate student in the Chemical Engineering Department of MIT, and I work in the labs of Professors Yetming Chang and Fakile Burchett. Today, I'm delighted to speak with you on a project that I've worked on understanding the physical characteristics of different weave patterns, specifically carbon cloth electrodes on redox flow battery performance. So when we think about the electricity that we get for our homes and our industries, they typically come from natural gas and coal sources. And for this grid pipeline, if we're interested in incorporating renewable options such as solar power and wind power, we're often met with a discrepancy in the supply and the demand of these energy timescales. Specifically, the sun sets, the wind stops, and when people come home from work, that the demand for electricity is higher. And so the strain of the grid during these peak hours is where we hope to be able to use these energy storage devices to implement these renewable options during this stress time. And in thinking about energy storage and its application, it really can come down to a time scale argument of the storage and delivery. In particular, in looking at different energy storage options, for example, lithium-ion batteries, while effective, they have short durations, for example, seconds to hours, which may not make them the most likely candidate for grid-scale energy storage. On the other end of the spectrum, pumped hydro has quite long duration, weeks to months energy storage, yet this requires a large body of water next to an elevation gradient in order to operate. Midway, though, are redox flow batteries with an hours to days type of energy storage and delivery, and that's really the focus system that our group works on, and as I'll be describing now. So there are many components to the redox flow battery, but in particular, it consists of a reactor with external tanks housing your electrolyte. This electrolyte consists of active species, supporting salt, and the solvent, which are pumped into the reactor to react. The electrolyte goes through a flow field which helps disperse the electrolyte onto the porous electrode where the redox reaction occurs. And finally, in between all of this is a membrane which helps in the shuttling of ions between the sides of the flow battery to help with charge neutrality. There are many advantages to the redox flow battery, such as decoupled energy and power scaling, energy scaling in that you can increase the volume of the tanks or active species concentration, and power scaling and you can increase the reactor size. These devices are simply manufactured as well as having low maintenance and can be location independent in setting these up anywhere and letting them run. As I mentioned, there are many components to the flow battery. What I'm going to be focusing my talk on, though, is that of the porous electrode and how that influences your flow battery performance, because it serves as the sites for the redox reactions, as well as the main area where there are pressure losses in the system. Porous carbon materials are typically used in flow batteries, specifically carbon papers, carbon cloths, and carbon felts. And these are repurposed from PEM fuel cell applications, though they found traction in flow batteries. In a recent study from our group, we were interested in looking at variations of the electrochemical performance and the fluid dynamic performance of different commercially available electrodes, such as papers, cloths, and felts. The results are shown here, where on the y-axis, we have the pressure loss of the electrode divided by the length, and on the x-axis, we have the current density for an IR-corrected 50 millivolt potential. And what we found was pretty interesting in that these carbon cloth electrodes exhibited the best of both worlds, having low pressure drop and high current densities. And we were curious as to why this was, and we posit that this has to do with the microstructure of these materials. The top distribution for this Mercury intrusion porosimetry plot is the frequency of the pores of a carbon cloth electrode relative to carbon papers. For the carbon cloth, there appears to be this bimodal-like distribution with pores at the around 100 micron pore diameter range, as well as pores at the 10 micron diameter range. And we hypothesize that it's these larger pores that help promote the advection of the electrolyte, resulting in lower pressure loss in the system, as well as these smaller pores, which help facilitate the mass transfer of active species from the bulk to the surface to react, which result in high current densities. But a limitation of the study is that we only looked at one carbon cloth, that in the green. In reality, there are quite a variety of carbon cloths that you can manufacture. Using a loom or larger industrial scales, you can create a myriad of different electrode structures, which all could have very different effects on the fluid dynamics and the electrochemistry. And that's really the guiding question for this project is how do these different weave patterns affect the flow battery performance? And so to start, AvCarb Material Solutions was gracious enough to provide us with 4 electrodes to use, all made from the same 7.5 micron fiber diameter. They were a plain weave pattern, an 8 harness satin, a second plain weave pattern, though the thickness was more than twice that of the red plain weave pattern shown here, in a 2x2 basket. And so clearly a number of structural differences stick out, one being the weave pattern that we see really from our vantage point in the through plane image here, as well as the thickness of these different electrodes. And so the question that we had for these materials was how does the morphology change between these woven structures at the microscopic level? And so again, we used Mercury intrusion porosimetry as our diagnostic technique to look at the different frequency of pore sizes for these 4 carbon cloths. What we found is that for all 4, there was this bimodal distribution that we had noted in the previous study. But focusing more on the distributions themselves, there are clear differences in particular to the frequency of the different pores available. And so because there is this variation of frequency of pores, with materials all having the same carbon fiber diameter and carbon fiber structure itself, we were curious as to the effect of the fluid dynamics and the electrochemical performance. To probe the electrochemistry, we used a single electrolyte non-aqueous flow cell at 50% state of charge for tempo radical tempo plus to measure different current responses to applied voltages. Additionally, as I mentioned, these materials have different thicknesses, and so to account for that, instead of using the same flow rate, we use the same electrolyte velocity, where we can normalize our flow rate by the electrode width and the thickness to get a consistent metric across the different materials. The results for the polarization are shown here for 1 centimeter per second electrolyte velocity and 5 centimeters per second. And what we found is that there's a different ordering in electrochemical performance for the 4 different materials. In particular, you can see this at the 1 centimeter per second, where there is a spreading of electrochemical performance. And this spreading and this ordering is consistent throughout different electrolyte velocities, yet at the higher velocities, there appear to be a sort of collapse of performance or marginal gains for these different materials. Apart from the electrochemistry, we were interested in the fluid dynamics as well. And using this setup shown in the top right, where we can pump acetonitrile through the electrode in our flow cell configuration and measure the pressure differentials for each electrode. Also considering the electrolyte velocities, again, to normalize for the thickness. So what's shown here is the pressure drop per length of electrode for each velocity. And we can, at least from the get-go, see what the different pressure values are for these materials, and that the 8 harness satin, the black, has the higher pressure drop versus the 2x2 basket, which has the lower pressure drop. But we can use these pressure drop measurements to extract more information by fitting to a Darcy-Forchheimer equation to pull out permeability values and Forchheimer coefficients for these different materials. And what's interesting that we found in this is that the pressure drop revealed the similarities in the woven structures, those seen at the larger length scale. In particular, the red and the blue are both plain weave patterns that exhibit the same pressure drop, permeability, and Forchheimer coefficient within statistical error, because what we believe is this setup does normalize for those different thicknesses, thus leaving just the macroscopic weave pattern that this pressure drop can capture. In addition to the fluid dynamics in EChem, we are interested in the surface area. And so to probe this, we looked into 4 different metrics to measure surface area of these electrodes. In particular, 3 ex situ measurements, BET, Mercury intrusion porosimetry, and a long fiber approximation, as I'm denoting as morphology here, as well as 1 in situ technique of the electrochemical double layer capacitance, where this is measured in the flow cell configuration for each electrode. From the get-go, we can get the 4 different volumetric surface areas for these different electrodes. And while there is a lot of information on this slide for the different values, what we noticed that was quite interesting is that the double layer measurements were more than an order of magnitude smaller than the ex situ measurements. As the double layer measurement is in situ and it is using the same advection flow pathways as done in the polarization and pressure drop measurements, we believe this shows that there is quite a discrepancy in the surface area available under flow relative to those measured in ex situ techniques. Additionally, we looked into the mass transfer specifically of these materials by reducing the active species of our tempo non-aqueous redox couple to get us into the mass transfer limiting regime using the same normalization again of the velocities. What I'm showing here is a plot of the limiting current that we can measure in this experiment, where from these limiting current measurements, we can put this into a known equation with geometric parameters as well as known chemistry values to extract this AKM value, which is the volumetric surface area, normalizing scaling the mass transfer coefficient. And from that, we can get these AKM values for different velocities to see what the relative scaling is between AKM and the velocity for these different materials. Though, interestingly, what we can also do is juxtapose this AKM value to the pressure drop per length of electrode that we had from a previous measurement. And what we find is that at these higher velocities, there seems to be a convergence on these more orthogonally based weave patterns, such as the red and the blue plane weave pattern and the 2x2 basket that is shown in the purple. And so this suggests that while similar macro properties in the weave pattern may converge at higher flow rates, that if they are different enough, there seems to still be some variation in the mass transfer and fluid dynamics. But generalizing these findings even more, we can use dimensionless correlations for comparing these metrics to other values both inside this study and for subsequent analysis with other carbon cloth electrodes. Specifically looking at the Sherwood number and the Peckley number, where the Sherwood number is defined by the AKM value that we can measure from the limiting current measurements, the characteristic length scale, and then divide by the volumetric surface area that we measured in our previous experiments, as well as the effective diffusivity. Now, there are a variety of length scales that we can choose, both physical with the fiber diameter, as well as fluid dynamically enforced through the half-power permeability and the Forsheimer scaling the permeability as well as the 4 different volumetric surface area measurements that we had before. We can use these to make a matrix of our different Sherwood-Peckley number relationships as shown here. And what's interesting to note is really just the order of magnitude difference based upon different length scale selection as well as surface area measurement. Though importantly, the scaling does not change per choice in length scale or effective diffusion. So we can get general guiding principles between the Sherwood number and the Peckley number scaling for these 4 different materials, though the choice of length scale and surface area can impact a prefactor for the Sherwood number and Peckley number scaling. So that's something to keep in mind for subsequent carbon cloth tests. And so in conclusion, we were able to show showing the differences in the microstructural variations of the different carbon cloths, as well as the different surface area measurements and how you can have a discrepancy using the double layer capacitance versus more ex situ techniques, which was the focus of another study. Additionally, that there need to be careful in the length scale selection for broadly generalizing the Sherwood number and Peckley numbers. But these are not the only modifications of electrodes that we can do. We can consider electrode compression as well as flow field selection for the interplay between structural deformation and fluid flow pathways. And with that, I would like to thank both Professor Burchett and Professor Chang, as well as their respective labs, for the fruitful discussions. I would also like to thank AvCarb, Micrometrics, and the Department of Materials Science and Engineering for the materials and spectroscopy, as well as the funding from J. Caesar, the Tau Beta Pi Graduate Fellowship, and the NSF Graduate Research Fellowship. And with that, I'm happy to take questions. And if you have any other questions that you'd like to ask that are offline, please feel free to email me at my contact information below. Thank you.